So today we're going to talk about the rotational partition function. Last time we did translation, and then next time we'll do vibration and electronic. I'm going to go through the rotational part. It's a pretty small equation and a pretty simple concept. Yes?
Was that lecture posted?
Mm-hmm.
There was no lecture posted.
Oh, really? On Blackboard? I'm sorry. Okay, well, I'll tell you the 2 or 3 equations you need to write down. Okay? Dropped the ball this week, apparently. So I don't have this, and I don't have a little question in top hat. So we're just doing the top hat attendance check, and then we'll do the equations. There's like 2 equations on the rotational partition function that you need to write down. Then you'll have this video that you can go through. I'll go ahead and post those handouts. And then I will also post the lecture notes on today's lab. So I'm going to go through a lecture on today's lab to kind of help you walk through it, because there's going to be so many people in there that this will get you a head start on it. Okay? So that's the plan for today. We'll do the rotational partition function, and then I'll talk through today's lab. Okay, so the rotational motion, remember that was a pretty simple energy equation that we had. It was B times J plus 1. So remember the different energy equations. You know, the energy for translation, or the particle in a box, was just N squared H squared over 8 ml squared, right? And in there we had our quantum number, our mass, the length of the box, okay? And it went as N squared. Well, the J, the energy equation for rotation, also, it looks kind of like it's linear in J, but it's not. It's J times J plus 1. So it also goes up as J squared. So the ramifications of that is that the energy spacings are not equal. Typically, we have mass in the denominator of our energy equations, and I don't see mass in here at all. That's because it's inside that B, that rotational constant. So if we expand B, we see this moment of inertia here. And that moment of inertia, I, is equal to the reduced mass times the distance squared of between the 2 atoms. That's for a diatomic. If it's not a diatomic, you just have the sum of all of the masses times their distance from the rotation axis squared. But anyway, the main thing I'm wanting to point out is that, again, mass is in the denominator of this energy equation too. So if you increase the mass, we'll see this today, if you increase the mass, then the rotational constant drops quite a bit. And so then the smallest mass for any diatomic that we would have would be hydrogen. Okay, so that makes sense. It's the lightest element on the periodic table. So H2 would be the smallest or lightest molecule. So it's going to have the largest rotational constant. And that's going to be an important concept for us today. And we'll see a couple of tables of rotational constants. So here's our partition function, our rotational partition function, and it's the sum of all of those Boltzmann factors. We have the degeneracy piece here, and so that is 2J plus 1 for rotation. So it depends on the quantum number. So as you go up in J quantum number, the degeneracy is a function. It goes up as 2J plus 1. And then for this energy equation, we put in the energy equation for rotation. And then we compare that to however much temperature we have in the room. So that's the temperature of the system. And this Boltzmann factor would define what thermal equilibrium is in that rotational system. Now, if we have a moderately high temperature, like room temperature, then we're definitely going to be able to integrate this rather than do a discrete sum. So we can integrate this with respect to J, because what we're saying there is, instead of adding up, 400,000 rotational energy levels, the difference between any one particular rotational level is insignificant. So that's a sort of a definition of infinitesimality. And so we can just go ahead and integrate this equation over J. And then we can even further simplify it at high temperatures. It just becomes this right here, this KT over HCB, or really just KT over B. But if we have B in wave numbers, KT is going to be in joules. And so if we take that joules and divide by Planck's constant and the speed of light in centimeters per second, that becomes wave numbers as well. And so we have this term, this temperature term, divided by this theta B, which is a new term for us called the rotational temperature. And so this is theta B and how it's defined. And so I think you should write down these two equations right here, that QR is equal to T over theta B, and then write down what theta B is. And if you want to be precise in your terminology, I should have put a little tilde on here. So that would be B is in wave numbers. And so now we can see how all of the units work out. So I have B in inverse centimeters times the speed of light in centimeters per second. So the centimeters cancel. Then I have a seconds from Planck's constant canceling per seconds in the speed of light. Then I have joules over joules in Boltzmann's constant, and then the Kelvin and Boltzmann's constants in the denominator. So it comes up top. So this is a temperature. So this theta B is a temperature. So it's just a way to convert the rotational constant in wave numbers over to some Kelvin that we're dealing with. And then we sort of compare that temperature of the room to this thermal or rotational temperature. And so since diatomic molecules are the smallest, we have that rotational constant, which has that moment of inertia in the denominator. For diatomics, that's mu r squared. For larger masses, it's this. Now, remember from the last time we had that note card bait equation that canceled all of these, or converted all these factors into a constant, a single constant. And so we had that 16.86 grams per mole angstrom squared wave numbers divided by the diatomic reduced mass and the distance between the two atoms. So we can look at these rotational constants, and if you want, these are in wave numbers, so if you want to put the little tilde on there to indicate their wave numbers, that's good. And so then diatomic hydrogen would be the largest possible value of B, because that would be the smallest reduced mass. And so here's our rotational constants here. So these are B's in wave numbers. And so hydrogen has a rotational constant of 60 wave numbers. HCl is 10 wave numbers. Notice that HCl has hydrogen on there. What if we make it a deuterium? We double that mass. Well, it pretty much cuts that rotational constant in half. And then last fall we did the iodine lab, where we were looking at the electronic spectra and we saw the individual vibrations. And I was talking about how there were rotational levels under that vibration, but we couldn't resolve them. Well, this is why. Look at the rotational constant for iodine. So the difference between those different rotational transitions would be, essentially 2B. Remember our 2B thing was going to be 0.04, essentially. So 0.08 would be the spacing of those peaks in wave numbers, which would be really, really small. So there's no way we could resolve that with our spectrometer. So we could use that Boltzmann constant to convert these to temperature. And so this piece right here, this is that one that you may not have memorized yet, but it's a good thing to memorize. That Boltzmann constant in terms of wave numbers is this 0.695 value. So you can take any rotational constant and divide by that Boltzmann constant in wave numbers per Kelvin, and you end up with the rotational temperature. So this says that even hydrogen, the smallest masses, the highest rotational constant, its rotational temperature is 87 Kelvin, which is pretty cold. So once we're above 87 Kelvin, we start to lose those quantum effects of rotation. And it just becomes a statistical population of rotational levels. And we really lose it when we're 10 times that theta value. So at 870, we would totally lose all of the rotational effects of hydrogen. And so let's look at iodine. So let's do 0.03 or 0.04. Let's just 0.04 wave numbers. Iodine. I2. Let's make it easy. This Boltzmann's constant, let's make it 0.7. Okay, can somebody do that real quick with their calculator? .057. Okay, so that's the rotational temperature for iodine. So when we get to 0.5, like 10 times that temperature, so 0.6 Kelvin, we've lost the quantum nature of rotation of iodine. So we're really not going to be able to see that rotational structure of iodine unless we have a really high resolution spectrometer. And so we were able to do that with at my in graduate school in my research advisor's lab. He had some really high resolution lasers, and we could see the individual transitions, rotational transitions for iodine. But he had 1,000th of a wave number resolution, and so we had quite a very expensive laser. I'll just leave it at that. So let's look at Gaussian output. So if we take this asymmetric molecule and we put it into Gaussian and we calculate the geometry optimization, and then we go on and do a frequency calculation in the thermochemistry section. Now that we're in thermodynamics, let's talk about that section of the output. We talked about vibrations last time. We had the IR intensity, the force constant, the reduced mass, the Raman spectroscopy. So we were simulating spectra using the frequency calculation in the last semester. This semester, we're going to use the thermochemistry output of that same calculation. So when you do a frequency calculation, you get this analysis in the end. And sure enough, you see it tells you what parameters you used for the calculation. By default, you're calculating it at room temperature, 298.15 Kelvin and 1 atmosphere pressure. You can, in the input of the Gaussian job, put a new atmosphere pressure, a new pressure, and a new temperature. So you could calculate different temperatures for your molecules. It has the default isotope masses. So the thing is, you're not calculating this this molecule with the mass on the periodic table. Look at chlorine; it's 35.5 roughly, and this is 34.96. So you're calculating the chlorine 35 isotope specifically. If you wanted to calculate the 37, you'd have to tell Gaussian use the lesser common isotope. It calculates your molar mass. So that's kind of convenient if you have a really big molecule. It's in there in Gaussian. It's the molar mass for this particular isotopic species, though. It's not the average molar mass. And then here we get into, there's some 3 dots there just to show, if you scroll a little further down, you see this rotational piece. And so this says this molecule is an asymmetric top. So an asymmetric top means that these 3 rotational constants are not equal. A symmetric top, either 2 of these will be equal or maybe all 3 would be equal. In a spherical type molecule, they would all 3 be equal. So if you think about a sphere, it doesn't matter which axis you rotate it along, right? So they're all 3 moments of inertia are equal in a sphere. And that would be an evenly weighted sphere, right? If you have a playground ball with a valve stem, it's not equally weighted. Have you noticed that? You try to roll a playground ball and it has some kind of weird motion. That's because it's not really a sphere. There's a defect on there that has a different mass. But if you have an equally weighted sphere, it doesn't matter what axis you roll it on, like a billiard ball. Wouldn't that be strange if you line the cue ball up with the weight on one side, like a valve stem? You could shoot around other balls if it was going the right speed. It'd be kind of cool. Now, a cylinder, obviously, it matters what axis you rotate it on, right? Because you've got an axis that it can roll on, and then an axis that it can't very easily, and so it makes a big difference. And so this right here would be a symmetric top. Okay, it has one unique axis, and then this axis is equal to this axis. So 2 of its rotational constants are equal. Now, this molecule is asymmetric because all 3 of its rotational constants are different. But sometimes you have what we call an accidental symmetric top, and that is when 2 of these are very similar. So this is 0.69 or 0.7, and this is 0.68. So both of them to one significant figure are 0.7. And that's just because this hydrogen is so small, it doesn't really change the rotational properties very much. So this looks very much like a diatomic, but it's not. Okay. So A is the 28. So that would be rotating around the chlorine-oxygen axis. That's the unique axis. If you're rotating around the chlorine-oxygen axis, then the heavy masses aren't moving very much, and so only the light mass is moving, and so that's going to be the biggest rotational constant. Remember, the smaller the mass is, the larger the rotational constant. And so that's just the hydrogen spinning around that oxygen. And so that would be the A rotational constant. The reason they don't label these X, Y, and Z is because A, B, and C map to X, Y, and Z in different ways. And so there's that's a little deeper topic than what we'll get to. But you can look at it and say, all right, I do know this is the largest rotational constant. So that's this motion around here. So that's the A rotation. So why do we call a rotational constant B for a diatomic? And that's because for a diatomic, if we just had an oxygen and a chlorine and no hydrogen, there is no, A is not defined, right? There's nothing off the axis, and so A is not defined. And then if you have the center of mass here, rotating around this axis, we'll call B, and then rotating around this axis here that's 90 degrees to that, we'll call that C. B is equal to C. And so we just, A is gone, so we get to B, and so we just call the rotational constant B. So for diatomics, we really have two rotational constants, but we can't tell the difference between B and C, so we just talk about B. Okay. But for an asymmetric top, A and B and C are all independent. So what's the energy levels for A? Well, it would be, the energy levels for this rotation would be equal to A times J plus 1. So we have energy levels of A, which is that hydrogen spinning around, and then we have the energy here, which would be B times J plus 1, and then C times J plus 1. So if we have three different types of rotations, we have three different energies that we can store those energies in this molecule. Yes?
I'm having a little bit of a hard time seeing the rotational constant.
Okay, so then let's go ahead and draw our axes. So this will be an axis coming out this way and an axis going this way. And I don't exactly know which one of these axes would be B and which one would be C. Okay, so I'm just going to say this one is B. So if we rotate the molecule around this axis, then that's B. And if we rotate it around this axis, that's C. Okay, now these are not symmetry axes. So if you're looking at this and saying that doesn't make any sense symmetrically, we're not talking about group theory or C2 axis or C3 axis. We're just talking about the molecule physically rotating around this axis.
So that the axis is essentially coming out of the screen?
Yeah,
okay,
yeah. And since you look at it and you go, but that's an asymmetric molecule, there is no axis there. There's no symmetry axis there, right? A symmetry axis, like on a methyl group, you have 3 spots, so that's a C3 axis, right? But we're just talking about rotation in space. We're not talking about symmetry. Okay, so this molecule can rotate around B, and it can rotate around C, and it can rotate around A. And we can store energy in those 3 locations.
And so a stupid question.
No.
If it can rotate around that bond between the chlorine and the oxygen, is there also rotation around the bond between the oxygen and the hydrogen, or is that so small?
Okay, no, that's a good question actually, because there's really, what we're really rotating around is the center of mass. Okay, and so that A rotation really isn't exactly on that, around that bond, but the hydrogen's so light, it might as well be. But that axis is probably just barely tipped over because of the weight of the hydrogen. Okay, and it's really rotating around that little bit of off axis, yeah. But that's great observations. But I hadn't really thought about, even though you didn't ask it, as I was explaining it to you, I thought, oh my goodness, what if they think these are symmetry axes? These are not symmetry axes. These are just rotational axes. Through the center of mass, the molecules spinning in space. And I can excite the A rotation independently of the B and the C. And in fact, we can tune, because they have different energies, we can tune certain spectroscopies to just one axis or the other. And so like the microwave oven is tuned to, and this happens, rotation happens in the microwave region typically. That microwave oven is tuned to one of the rotations in water. Water's an asymmetric top. It has A, B, and C rotational constants. And I don't remember which one it's tuned to, but that so and so many gigahertz microwave radiator in your microwave oven is tuned to water to make it spin. And so water's in your food, and it's trying to get loose because this gigahertz thing's trying to spin it, and it's banging into the molecules of your food and heating them up. So the microwave's absorbed by the water, and the water bangs into your food and heats it up. So that's the way the microwave works. It's totally radiative. It's not convective, and it's not what's the other option? I don't know. We'll get to that, but it's a radiative heating. So that's why they used to talk about, we're using radiation to heat your food, when the microwaves came out in the 70s, and it scared everybody. They're like, oh, it's microwave radiation. So these are rotational temperatures. So I wanted to explain what a rotational temperature was on the previous slide. So when you get to Gaussian, you'll understand what that's talking about. And then here's the rotational constants in gigahertz. Okay. And so if you wanted to convert those, so this would be gigahertz. Okay, which is 10 to the 9th seconds to the minus 1. And it's 30 wave numbers per gigahertz. And that'll convert it to wave numbers. Now, just for grins, you do this on your time, okay? So I'm saying prove that this is c, the speed of light. Okay, so just have fun with that. Okay. So here for our largest rotational constant, we can convert that over, and it's 19.9 wave number. So we would be able to resolve that h spinning around this OCL in our infrared spectrometers. So that's a gaseous bleach. I don't know if that's anywhere in the presence of water. I don't know if it would actually have a vapor pressure of that, but it would be fun to try to get the spectrum of that molecule. Okay, here's the rotational temperature, 28.63. I'm just verifying what Gaussian is showing us. Okay, so we're coming up on 30 minutes. I'm going to try to speed up a little bit. We've covered the equations that I want you to know, that rotational temperature and the rotational partition function. So here's for symmetric molecules, we have a couple of other factors that come in, and this is for three-dimensional partition function. We have three of those temperatures, three different rotational temperatures. It's to the square halves. It has this pi in front, and this thing right here, the symmetry number. And so that's to prevent overcounting. Remember, we're dealing with probabilities. And so if we have, in our normalization case, certain levels that really aren't truly different events, then we need to reduce that denominator a little bit. And so this is adjusting that denominator, that normalization part, so that we get accurate statistics. Okay. So let's look down now at the partition function. We have reported to us in Gaussian the actual rotational partition function. Okay. So where does that number come from? Well, we have our equation here. This is an asymmetric top, and so it says the rotational symmetry number is 1. So that's equal to sigma. So this guy right here is 1. And so we can put all of these numbers in here. We're at 298 Kelvin. We have our 3 rotational temperatures. Temperatures cubed, and we divide those by those rotational temperatures, take the square root, multiply by the square root of pi, and we end up with 2,467. And is that, does that match what Gaussian tells us? Well, we could move that decimal place to the left 4 places and make it times 10 to the 4th. But notice how this is really a weird way to write scientific notation. And they're using a D here. So you might see that in Gaussian and go, what is a D? Okay, it's strange. Well, they wanted, and this is sort of ancient, okay, compared to our modern day computing. Gaussian was written in Fortran back in the 60s and 70s, and they wanted to, have a shorthand for exponentiation in times 10 to the 4th or what have you. And they didn't want to use E because E was like an exponential function. And so they used D. But somehow we've switched over, and in Excel, if you were to write this number 0.247, blah, 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 E plus 4, it would take that in as a number, and it would take that E plus 4 as times 10 to the 4th. So you can enter big numbers like that. Avogadro's number in Excel, if you were to write 6.022 E23, then that would show up as 6.022 times 10 to the 23rd in Excel. So I don't know about D. I don't know if Excel would recognize D, okay? But Gaussian uses D, and also their sort of floating point or scientific notation has all zeros in the front, so they don't keep one digit in front of a non-zero number. They push them all to the decimal places. Strange. Don't know why. It's just historical. That's how they programmed Fortran, and if it ain't broke, don't fix it. So they just left that stuff alone. So some of this stuff goes back to the 60s and 70s. Yeah, so kind of interesting. But anyway, now let's talk about what this really means. Remember the partition function. What you tell me, this is our engagement part of the class, right? You tell me what that partition function represents. What do you say? Yeah, so it's the normalization constant, the denominator in a probability calculation. What's another way I've described it? What if we cool it way down? What is its minimum value? Does it go to 0 or something else? We did this last time, so this is a review on Friday. Goes to 1. So what does that mean when it goes to 1? If we cool it down to almost absolute 0, it goes to 1. What does that mean? What is Q telling us?
If it's a probability, isn't 1 like 100%?
Yeah, but it's the denominator in the probability calculation. So it's telling us there's only one energy level that can be populated at that temperature, right? So there's only one possible event, and that is the ground state is populated. So Q seems to be telling us how many possible energy levels we could be in. At really low temperatures, it's just one. There's only one level possible, the ground state. At high temperatures, in this case, at room temperature, for a rotation of this molecule, there are 2,467 possibilities in our probability calculation. That's the total number of energy levels, if you want to think of it that way, that are going to be populated at room temperature. So if we calculate a probability of any one level, the denominator is going to be 2,467. So if I pick a rotational level and say, what's the probability of being in that rotational level at room temperature, and then we have to always use this phrase, all other things being equal, the probability would be 1 out of 2,467. Right? The denominator is the total possibilities of energy levels being populated. Remember, for translation, it was something times 10 to the 30. So picking a translational energy level, it would be one level possibility out of 10 to the 30 possibilities. So we can store a whole lot more energy in translation because there's more options at a given temperature. Rotation, we can store in this particular molecule, we have 2,467 energy levels where we can put molecules and store energy. Okay. Look at vibration. This one is essentially 0.1 times 10, so 1. So we're really not very excited in terms of vibration. Electronic, 0.1 with all those zeros times 10, so it's 1. So at this temperature, room temperature, we haven't excited this molecule electronically at all. So we're in a ground electronic state. We have 2,000 possible rotational states. Translation, we have times 10 to the 8, right? So we have a lot of translational states that we can populate. So here's just a plot of the rotational partition function. Again, it goes up as temperature goes up. So let's jump into the lab. This is a fun lab. I really enjoy it. I'm going to go ahead and stop this video and make a